I'd like you to recall Ohm's law, which told us that the potential difference is equal to the current times the resistance. Okay, so for objects for which the resistance is the defining property, this relationship is true. So notice that if we have a conductor following the perfect conductor rules, then we need to have delta V equal 0. And if some current is flowing, then that would tell us that delta V being 0 would have to imply that the resistance is equal to 0. But we know for real conductors that the resistance is not 0. Real conductors have some small amount of resistance. So in reality, let's say that we have some wire, and the resistance for the wire will depend on the wire, obviously, but it could be something like 0.01 ohms for a very low resistance wire, or maybe up to 1 ohm for a more resistive wire. Typically, wires are going to be sort of in that range. All right, and so let's say that we also had some reasonable current going through a wire. So in a typical circuit for an everyday object, maybe the current would be something like 0.1 amps. Okay, so that seems like a perfectly ordinary amount. So if I use Ohm's law, delta V equals IR, well, if I have, let's say, 0.1 amps, just to pick a number, and 0.1 ohms for some ordinary wire, then what is the potential difference across the wire? Well, if you just calculate that out, you get 0.01 volts. And based on the potential differences in a normal circuit where you have a battery that's like 1.5 volts or something, 0.01 volts is going to be really small compared to that. So something like 1%. So if you're just trying to understand what a circuit is doing, typically the resistance of the wire is something you'll be able to ignore completely. But notice that while this is small, it's not quite 0. All right, so sometimes this will be important. Okay, so we can usually assume that the delta V is just 0 unless we have some reason why the other resistances in the circuit are also really, really small. Okay, so one example would be, let's say you just took a battery, and I don't recommend you do this. So if you took a battery and you just connected the two ends with a single wire, well, you kind of run into a contradiction based on the rules that we have for ideal batteries and ideal wires. Okay, so if I have a battery like this, then the rule is that the delta V is equal to 1.5 volts. Okay, that was the rule for a battery. But if I just connect the two ends with a wire, well, the rule for the wire is that delta V equals 0. So I get a contradiction. I can't have a potential difference of 1.5 volts and also have a potential difference of 0. They have to agree. Whatever the truth is, it needs to be one or the other. And the answer is that, well, the delta V across the wire is not actually 0, it's just usually small. And so if we assume that there's some small resistance for the wire, so wires have a small resistance, it turns out so do batteries, which we'll talk about later. So what that means is that we no longer have to rely on that rule. So going back to delta V equals IR, well, we assumed that the delta V was really small because we assumed that the R was really small. But if we have an R that's not small compared to everything else in the circuit, and we have a delta V that's some reasonable size, then we can have this equation still be true if the current is really big. Okay, so something like a volt could be 1 ohm times 1 amp, or it could be 0.01 ohms times 100 amps. So essentially, you'll just get a really big current in a case like this. Typically, we can get away with just using the ideal battery and wire rules. So batteries are at a constant potential difference, wires are at a constant potential, and that usually doesn't run into any problems. It's only if you set up a circuit like this one where you connect two ends of a battery together, for instance, that you need to worry about the resistance of the wire.